This is Transition Metal Chemistry. Chapter 7, An Introduction to Coordination Compounds. In this chapter, we will cover 4 different topics. The first topic is the language of coordination chemistry. This topic includes 2 sections. First, the names of the ligands, and then the names of the transition metal complexes. The second topic is the constitution and geometry of the transition metal complexes. We will look at different coordination numbers. That means a transition metal center can be bonded to a different number of ligands. Also, we'll look at polymetallic complexes. In this kind of complexes, a ligand may be bonded to multiple transition metal centers. The third topic is isomerism and chirality. You learned some of this in organic chemistry. So we'll look at the isomers of all these transition metal complexes, and also we'll look at the ligand chirality and the chirality of the transition metal complex. And finally, the thermodynamics of complex formation. So we'll look at the enthalpy change and the entropy change when a transition metal complex is formed. So first, Section 7.1, Representative ligands. There are all different kind of ligands, and we can categorize them by the number of points of attachment to the metal. For example, we have monodentate ligands, bidentate ligands, and tridentate ligands. Monodentate means one-toothed. So that means this kind of ligands have 1 point of attachment to the metal, like water, ammonia. So we know ammonia has 1 pair of electrons that can be donated to the metal. But water has 2 lone pairs. However, because these 2 lone pairs are pointing into different directions with a very large angle of roughly 106 degrees. So it's impossible for water to form 2 bonds with a transition metal. So usually a water can only form 1 bond with a transition metal center. Bidentate. This is one example. This is aceto, acetonato. So aceto is CH3CO functional group. Acetonato is actually acetonate. So this is the negative ion of acetone. So in this case, the 2 oxygen atoms in this ligand can both form a bond with the same transition metal center. So this is a bidentate ligand. Now we have tridentate, diethylene triamine. So I will show you the structure of this ligand. But when you see triamine, you know there are 3 nitrogen atoms in this ligand. Each of these 3 nitrogen atoms can form a bond with the same transition metal center. So therefore, this is tridentate. So if you have bidentate, tridentate, tetradentate, etc., overall we can call them polydentate. That means more than 1 donor, more than 1 electron donor to the transition metal center. There's also a kind of ligand which is special. They're called ambidentate. For example, if you have NCS minus or SCN minus, they have the same molecular geometry, but the negative charge, you can place that negative charge on nitrogen or on sulfur, because you can write different resonance structures. And then this nitrogen can be bonded to the transition metal center. The sulfur can be bonded to the transition metal center. So in this case, we call this ligand ambidentate. The name of this NCS minus is thiocyanato, but just to specify the point of attachment, we introduce a Greek letter kappa here. So if you say it's thiocyanato kappa N, that means nitrogen is bonded to the transition metal. If you say it's kappa S, that means sulfur is bonded to the transition metal center. Some neutral ligands have special names in transition metal chemistry. Water is not called water in transition metal chemistry as a ligand. Water is called aqua. Ammonia is called amine. Carbon monoxide is called carbonado as a ligand in transition metal chemistry. For most anionic ligands, we need to replace their ending E of the general names with letter O. So if you see IDE in the end, you need to replace IDE with IDO. For example, if you see chloride, chlorine minus is called chloride in general chemistry. In transition metal chemistry, as a ligand, you need to replace this E with O, and you need to say this is a chlorido ligand. Similarly, when you see ATE in the name of oxo anions, you need to replace the last letter E with O. If you see ITE, it becomes ITO. Now, I'm going to give you many examples here. So first, fluorine minus, chlorine minus, bromine minus, iodine minus. They are called fluoride, chloride, bromide, iodide in general chemistry, and in transition metal chemistry, they have a similar name. You just replace the ending E with O. Now they are called fluorido, chlorido, bromido, and iodido. There are also common names. So if you hear people say the ligand names are fluoro, chloro, bromo, and iodo, they are all correct as well. It's just these are the common names in transition metal chemistry. These are the UPAC names. All right? And these are the general names. For example, in general chemistry, we call them fluorido, chlorido, bromido, and iodido. This is a cyanide in general chemistry. Now it becomes cyanido in transition metal chemistry. And the common name is cyano group, cyano-functional group. In organic chemistry, we call that cyano-functional group, CN cyano-functional group. So we can still use that common name in transition metal chemistry, but the UPAC name is cyanido. With oxygen, the general name ends with ATE or ITE, depending on the number of oxygen atoms. So in this case, it's called cyanate. There's only one possible oxo anions for this kind of structure. You can't have O2Cn minus. So the UPAC name is cyanato. You can see I just replaced E with O. SCN. So if you compare this to, when we replace oxygen with sulfur, you need to add a prefix, thio, Thio, thio. So it's thiocyanate. As the general name, as a ligand, it's thiocyanato. This is just hydride. So if you have NaH, sodium hydride, but in transition metal chemistry as a ligand, it's hydrido, hydroxido. The common name is hydroxyl. Oxygen 2 minus. So if you have a ionic compound MgO, it's just magnesium oxide, but in transition metal chemistry as a ligand, it's called oxido. The common name is oxo. Sulfur, sulfide, sulfido. R can be any functional group. Rs minus is thiolate, but in transition metal chemistry as a ligand, it's thiolato. This we know it's carbonates, but in transition metal chemistry, carbonado. Oxalate, oxalato. This one is just COO minus bonded with another COO minus. The bond is between the two carbon atoms. This one, acetonate. So this is just the negative ion of acetone. The ligand name is acetonato. Okay, acetonato. This is aceto or aceto. Now this is the conjugate base of glycine. So it's called glycinate. The ligand name is glycinato. This is just nitrate. The ligand name is nitrato. This is nitrite with one less oxygen than nitrate. So this is nitrite. More oxygen, ATE, less oxygen, ITE. In transition metal chemistry, this ligand is nitrito. And then in this ligand, you can have nitrogen bonded to transition metals, and then you say it's dash copper N. If oxygen is bonded to the transition metal, then it's dash copper O. Common name is nitrito. So if the nitrogen is bonded to the transition metal, you can still call this nitro. It comes from organic chemistry, the nitro functional group. Nitrito over here, if you don't specify kappa N or kappa O, by default, or say maybe it's just bonded to the transition metal via the oxygen point of attachment. Now I want to show you the structures. This is aceto, acetonato. So aceto means you have CH3, COO. Acetonato is simply CH3, COO, and then over here another supposedly CH3. You get a acetone, but this is the conjugate base of acetoacetone. So there's a negative charge here. And if you have this CH2 minus charge here, it's not stable. And then we need to write out a more stable Lewis structure. This CH2 now becomes CH minus. So one proton will be given here. So you have COO, CH minus, and over here another COO. And then this negative charge on CH minus can be delocalized on these two oxygen atoms, and that's why we draw this structure with this curvy line. That means this negative charge is delocalized on this carbon, on this oxygen, and on this oxygen. The abbreviation is AC minus. The first AC is aceto. The second AC is from this conjugate base of acetone. All right. The donor atoms are oxygen. There are two of them. So both oxygen atoms can form a bond with the same transition metal center right here. And you can see if I place a transition metal center here, it's going to form a 6-membered ring. It's pretty stable. This is amine. Again, it's ammonia, but in transition metal chemistry, we'll call that amine. The donor atom is nitrogen. There's only one donor, water. Again, despite the two lone pairs, there's only one lone pair from the oxygen that can form a bond with the same transition metal center. Is it possible for this water molecule to form two bonds with two different transition metal centers? Well, that's possible. Again, transition metal chemistry, as a ligand, we call this aqua, not water. We call that aqua. 2,2 bipyridine. So you have two pyridine molecules. Over here you have position 1. So these two are position 2. This is position 1. I think this is position 2. The abbreviation is bipyridine. The donor atoms are these two nitrogen atoms. There are two donors. Bromido, that's easy. Carbonado, that's easy. It's just carbonate. Although there are three oxygen atoms in this Carbonado ligand, only one or two oxygen can be bonded to the same transition metal center. Because again, the three oxygen atoms are separated from each other. They are far away from each other in space. So it's unlikely for this three oxygen atoms to form a bond with the same transition metal. But if you have multiple transition metal centers, it's possible for this Carbonado to form three bonds. Carbonyl. This is actually carbon monoxide. In transition metal chemistry, it's called a carbonyl ligand. Over here, it's very important for you to realize, in this case, it's the carbon, not the oxygen, that forms a bond to the transition metal. We'll talk about this later, but if you can draw the Lewis structure of this carbonyl ligand or carbon monoxide, you'll realize the negative formal charge is on carbon. The oxygen bears a +1 formal charge. So really it's easier for the carbon to donate its lone pair electrons to the transition metal. Chlorido, that's easy. This one, there are 6 oxygen atoms in the ring. So this is the UPAC name, the positions of the oxygen atoms. Hexa, that means 6 oxygen atoms. In cyclooctadiene, octadiene, that means 18. So supposedly we're looking, if you just say cyclooctadiene, that means 18 carbon atoms in this ring. But then you have hexaoxa, that means 6 carbons are replaced by 6 oxygen atoms. And then we specify the positions of the 6 oxygen atoms, 1, 2, 3, 4, and then 7 and 10, and then 13, and then 16. I think they missed 16 here in the textbook. The common name is 18 crown 6 because if you draw the 3-dimensional structure of this, it does look like a crown. All 6 oxygen atoms can be bonded to the same transition metal. Just imagine a transition metal center here. It can form 6 bonds with the 6 oxygen atoms. But again, I want to tell you this: the real structure is not a planar structure. It's a 3-dimensional structure that looks like a crown. This is even more complicated. But really, we just need to look at the atoms that can donate electrons to the transition metal center. There are 5 oxygens and 2 nitrogens. All of them can donate electrons to the same transition metal center. Cyanado, this is easy. Diethylene triamine, this is commonly used. we have actually the structure is this. It's NH2, and then CH2, and then NH, and then CH2, and then NH2 again. So this is a very long chain. On the two ends of the chain, you have two amino groups. In the middle, you have another NH. All right, between two amino groups, you have CH2. So because you have two such CH2 functional groups, we call that diethylene. Triamine, because you have three amino groups. The three nitrogen atoms can form three bonds with the same transition metal. The abbreviation is diene. That means diethylene. Over here, the naming of this is really interesting. It's called a bis diphenylphosphenoethane. So this by itself, you can call this diphenylphosphine. And then we replace the last letter E with O, so diphenylphosphino ligand. We have two of them. So supposedly we just say, if we have two such ligands, usually we say diphenylphosphino. But if you say di, it just sounds really weird. So in transition metal chemistry, if you have a very complex ligand, and then you have two of them, we say bis. If you have three of them, we say tris. If you have four of them, we say tetrakis instead of tetra. So we convert di to bis, tri to tris, and tetra to tetrakis. What about 5 ligands, 6 ligands? Well, if you have a very complex ligand name, we say pentakis. All right, and so on. So over here, both phosphorus can donate electrons to the same transition metal. This one, okay, you just have CH2 here instead of two CH2s. So this is bis diphenylphosphanomethane. Similar structures. This is a anionic ligand. It's Cyclopentadiene. This is actually a aromatic ligand. So you have two double bonds. They contribute 4 pi electrons, and then you have a CH minus. This CH minus also has 2 p electrons that occupy the p orbital. So you have 2 p electrons and then 4 pi electrons. Together you have 6 p/pi electrons that can form this aromatic ring. All right. There's a similar ionic aromatic ring. If you have carbon 7, hydrogen 7 plus, and then it's also aromatic. In carbon 7, hydrogen 7 plus, you have 3 double bonds, 3 conjugated double bonds, and then you have a CH plus with an empty p orbital. So in that case, you have just 6 pi electrons. All right, so the abbreviation is Cp minus. All 5 carbon atoms can donate electrons to the transition metal, so there are 5 points of attachment. But later you will see it's not always 5. Sometimes you can have 1 or 3. Those are rare cases. I just want to tell you it's possible. In most cases, all 5 carbons form a bond with the same transition metal. 1,2-diaminoethane. So this is just ethane with 2 functional groups. So that's why it's called a 1,2-diaminoethane. The abbreviation is En. Both the nitrogen atoms can donate electrons to the same transition metal. This structure is probably introduced in quantitative analysis. because EDTA is a very commonly used ligand in analytical chemistry. The name is ethylene, so you have ethylene here. Diamine, so diamine here, ethylene diamine, and each nitrogen is bonded to two acetates. So a total of 4, okay, a total of 4. So that's why the name is ethylene diamine tetracetato in intrinsic metal chemistry. The 4 negative charges, so it's EDTA 4 minus. These two nitrogen atoms can donate electrons to the intrinsic metal at the same time, because you have 4 COO minus, right? So on the end you have O minus, O minus, O minus, O minus. They can also donate electrons to the transition metal. Therefore, the 2 nitrogen and the 2 oxygen can all donate electrons to the same transition metal at the same time. So this single ligand can have 6 points of attachment to the transition metal center. And again, I just want to remind you, this is just a 2-dimensional picture of this ligand. Later I will show you the 3-dimensional structure. Fluorido, that's easy. This is just the conjugated base of glycine. Both the nitrogen and one of the 2 oxygen can form 2 points of attachment to the transition metal. Hydrido and hydroxide, they are easy. Hydrido, easy. Nitrato. This is just a nitrate in general chemistry. And again, because the 3 oxygen atoms are far away from each other, it's possible to have only 1 or 2 oxygen atoms bonded to the transition metal. Nitrito, kappa N, nitrito, kappa O. So that means nitrogen can be bonded to the transition metal. Oxygen can also be bonded to the transition metal. The common names of this is nitro. The common name of this is nitrito. We have more structures. Oxato, oxalate becomes oxalato. Okay, this is oxalato. The abbreviation is OX2 minus. Pyridine, so this is just pyridine. This nitrogen has a lone pair here, Sulfido from sulfide. Cyclotetradecaene. Tetra means 4, deca means 10 carbon. So this, if you just say cyclotetradecaene, it's a 14-membered carbon ring. But then aza means you need to replace a carbon with nitrogen. And then you have tetraaza or tetraaza. That means 4 carbon atoms will be replaced by the nitrogen atoms. Alright, so the position should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14. Alright, so 14 membered ring. And the position 1, 4, 8, 11. So supposedly you should, specify the positions here. These 4 nitrogens can form 4 bonds with a transition metal, either in the ring or above the ring. Thio, that means you need to replace a oxygen with sulfur. So thiocyanate kappa N, that means nitrogen is bonded to the transition metal. Thiocyanate kappa S, sulfur is bonded to the transition metal. Thiolato comes from thiolate, RS minus, thiolate. Triamino, that means 3 amino groups, triamino. And then triethylamine, another amine here. So this is that amine, triethylamine. So if you have just nitrogen bonded to 3 ethyl groups, that's triethylamine. But then on the end of the 3 ethyl groups, you replace 1 hydrogen with an amino group. So it's triethylamine. The abbreviation is TREN, tren. So all these 4 nitrogen atoms can form a bond with the same transition metal. All right. So this is tetradentate, four teeth. Tricyclohexylphosphine. So really it's just 4 cyclohexenyl groups bonded to this phosphorus atom. The abbreviation is PCY3. I want to remind you of the steric effect here. This phosphorus is bonded to 3 cyclohexenyl function groups. So those are just cyclohexanes. And then you remove 1 hydrogen atom, and then you have this carbon bonded to the phosphorus. The phosphorus has 1 lone pair that can be used to donate to the transition metal. Over here, you just replace this cyclohexenyl group with a methyl group, much smaller methyl groups. Abbreviation is just PME3. And also, you can just replace this cyclohexenyl group with this is phenyl groups. So 3 phenyl groups here. So triphenylphosphine. Over here, so asterisk here. The PR3 ligand is formally a substituted phosphine. So it's like methane, silane, so it's phosphine. But the older nomenclature based on the name phosphine is widely used, so we're using phosphine here. Supposedly, when you see CH4, it's methane. So when you see PH3, should be phosphine. But then, in the old days, it's phosphine, so we're using those here. Many organic ligands just keep their common names in organic chemistry. So if you see a pyridine as a ligand, just call that pyridine. The abbreviation is PY, and 2,2-bipyridine is just 2,2-bipyridine. For simplicity, you often see BPY. That means bipyridine. 2,2' will tell you the positions of the linkage and the positions of the nitrogen atoms in the pyridine structure. Ethylene diamine, so this is ethylene diamine, or you can name this 1,2-diamino ethane. So really it's just ethane with 2 functional groups. 2 amino functional groups. So another name is just 1,2-diamino ethane. All right. So and then this is diethylene triamine. So this is ethylene, diethylene, and then triamine. Abbreviation is DIEN. So diethylene. Triethylene tetraamine. So you can have 3. Ethylene, so they are not really ethylene, they are actually CH2 with a single bond in between, but we can see this as the same molecular formula as ethylene, so it's triethylene, 3 of them, and then tetraamine. There's also TREN, TREN, you saw the structure of this. Triamino triethylamine. So if you look at this triethylamine, it's just ammonia, NH3, with each of the 3 hydrogen atoms being replaced with a ethyl group, and then you have nitrogen bonded to 3 ethyl functional groups, and then at the end of each ethyl functional group, you replace a hydrogen with an amino group. So then you have triamino triethylamine. The abbreviation is TREN, TREM, with 4 points of attachments. You have 1 nitrogen here, and then you have 3 nitrogen atoms here. Again, these are actually substituted phosphine, but the older names are just substituted phosphine. So we're going to use the old names. PCY3 tricyclohexaneophosphane, trimethylphosphane, triphenylphosphane. And over here you can see this ligand has two same such functional groups. This is diphenylphosphino. Since we have two of them, supposedly we should say diphenylphosphino, but that does sound weird. So we'll just use bis, tris, tetrakis, pentakis instead of di, tri, tetra, and penta. So over here we say this is a bis. There are two such ligands here. So bis diphenylphosphino ethane. And this is bis diphenylphosphino methane. This is really long name here. It's just, I would just say 18 crown 6. That means this is a 18 member of the ring with 6 carbon atoms being replaced with 6 oxygen atoms. 1, 4, 8, 11 tetra-aza cyclotetradecan. Cyclo, that means it's a ring. Tetra, that means 4. Deca, that means 10. Tetradeca, that means 14. Tetradeca-N, that means 14 carbon. Cyclo tetradecan, that means a 14 membered ring. And then tetra-aza means 4 carbon atoms will be replaced with 4 nitrogen atoms on these 4 positions, 1, 4, 8, 10, 11. So I want you to be able to picture those structures in your head. Organic and ionic ligands, cyclopentadiene, this is a aromatic ring. Carbon 5, hydrogen 5 minus. Again, this is because you have 4 conjugated pi electrons, and then you have a CH minus with a p orbital occupied by 2 p electrons. So these 2 p electrons join the other 4 pi electrons to form a cyclic conjugated network that consists of 6 pi electrons. Okay, now you can view those 2 p electrons as pi electrons as they take part in the conjugated network. So there are 6 pi electrons in this anionic carbon ring structure, 5-member ring structure. EDTA, ethylene, diamine, tetraacetato. Now I'm going to show you the 3-dimensional structure here. This is the transition metal M. But in my lecture notes, sometimes you will see TM, transition metal, instead of just M. All right. So this transition metal is bonded to 4 oxygen here, and then 2 nitrogen here. All right. This transition metal complex is extremely stable. We call this a chelate. Okay, a chelate. So the same ligand may form multiple bonds with the transition metal, and the additional stability, naively you would say, comes from the 6 bonds. But really, it's due to the entropic effect. The entropic effect of the formation of the chelate structure. We will get back to the chelate effect or entropic effect or entropy effect a bit later near the end of this chapter.